James Webb will go where no other telescope has gone before.
You know, we've recognized when we look at these beautiful images that we really are looking back at our origins.
What exactly is at the edge of the universe? While there is a very slim chance that humans will ever physically reach the edge, we have got a powerful set of eyes in deep space that's helping us see far away. The James Webb Space Telescope, which has just announced what is at the edge of the observable universe. How wide is the universe? The universe is an incredibly vast and mysterious place, and its size is something that's fascinated scientists, philosophers, and curious minds for centuries. While the spatial size of the entire universe is unknown, it is possible to measure the size of the observable universe, which is approximately 93 billion light-years in diameter at the present day. But what does this number really mean? To put it into perspective, a light-year is a unit of distance used in astronomy and is equivalent to about 5.88 trillion miles or 9.46 trillion kilometers. This means that the observable universe is approximately 546.84 billion trillion miles, or 878.58 billion trillion kilometers in diameter. That's a mind-bogglingly large number that's difficult to even comprehend. But why is the universe so big? The answer to this question lies in its origins. According to the Big Bang Theory, the universe was created around 13.8 billion years ago in an explosive event that caused it to rapidly expand. Since then, it has continued to expand at an accelerating rate driven by mysterious forces such as dark energy. As the universe expanded, matter began to clump together under the influence of gravity, forming stars, galaxies, and eventually planets like our very own Earth. Over time, these structures grew larger and more complex, giving rise to the incredible diversity of objects and phenomena we see in the universe today. But within all of this expansion and growth, the universe is mostly empty. In fact, if you were to shrink our entire solar system down to the size of a quarter and the rest of the universe at the same ratio, the nearest star to our sun would still be 2 soccer fields away. And that's just within our own Milky Way galaxy, one of billions of galaxies in the observable universe. However, when talking about the edge of the universe, it's important to understand a concept: the observable universe. The universe with a capital U refers to everything that exists, has existed, or will exist anytime, anywhere, regardless of whether or not we are aware of it yet or ever will be. This includes all matter and energy as well as space and time itself. The true size and shape of the universe are still unknown, and it's possible that it may be infinite. On the other hand, the observable universe refers to the region of space that we can actually observe from Earth or its space-based telescopes and exploratory probes at the present time. This includes all matter that can be observed from Earth, including stars, galaxies, and other celestial objects. The observable universe is a spherical region centered on the observer, and its size is determined by the distance that light has been able to travel since the beginning of the universe. So what's the difference between these two concepts? Well, in short, the observable universe is just a small part of the entire universe, the part that we can see and study. While the true size of the entire universe is still unknown, we can measure the size of the observable universe, which is approximately 93 billion light-years in diameter. But why can't we see the entire universe? Well, there are several reasons for this. First, light takes time to travel through space. This means that when we look at distant objects in the universe, we're actually seeing them as they were in the past, not as they are now. The farther away an object is, the longer its light has taken to reach us. Secondly, the universe is expanding. This means that distant objects are moving away from us at an accelerating rate. As a result, their light is stretched out and redshifted, making it more difficult to detect. Eventually, these objects will move so far away that their light will no longer be able to reach us. Now, the concept of the edge of the universe is a fascinating and complex topic that has puzzled scientists, philosophers, and thinkers for centuries. There are several theories about what lies at the edge of the universe, but the truth is that we do not yet have a definitive answer. One theory is that the universe is infinite and has no edge. This theory is based on the cosmological principle, which states the universe is isotropic, meaning that it looks roughly the same in every direction. If this principle holds true, then it would imply that the universe goes on forever and thus has no edge. Another theory is that the universe is finite, but also has no edge. This theory proposes that the universe curves back on itself, like the surface of a ball, and so has no edge. In this scenario, if you were to travel far enough in any direction, you would eventually end up back where you started. Yet another theory is that our universe is just one of many in a larger multiverse. In this scenario, there could be other universes beyond our own, each with its own laws of physics and properties. These other universes could be completely separate from our own, or they could be connected in some way. And with the JWST, we have a way to look far back both in time and into the universe. And one of the satellite's most remarkable discoveries is the identification of the earliest strands of the cosmic web, a vast network of galaxies and filaments that spans the universe. The cosmic web is the result of gravity pulling matter together over billions of years. It consists of dense regions of galaxy and gas called nodes or clusters, connected by thin bridges of matter called filaments. Between these structures are large empty spaces called voids. The cosmic web is the largest scale structure in the universe, and it reveals how matter is distributed and how galaxies evolve. The cosmic web started out as tiny fluctuations in the density of matter in the early universe, soon after the Big Bang. These fluctuations grew over time as gravity amplified them, creating regions of higher and lower density. The higher density regions collapsed into galaxies and clusters, while the lower density regions expanded into voids. The filaments formed along the boundaries between these regions, acting as conduits for gas and matter to flow into the clusters. And the James Webb Space Telescope has detected some of the earliest filaments of the cosmic web, using its powerful infrared vision to peer back in time. In a study led by Feiger Wang of the University of Arizona in Tucson, astronomers used the James Webb Telescope to observe 25 quasars that existed within the first billion years after the Big Bang. Quasars are extremely bright galaxies that host supermassive black holes at their centers. They are ideal targets for studying the early universe because they can be seen from very far away and they can illuminate their surroundings. Among these quasars, Webb discovered a thread-like arrangement of 10 galaxies that existed just 830 million years after the Big Bang. The 3 million light-year-long structure is anchored by a luminous quasar called J03053150, whose brightness outshines its host galaxy. The other 9 galaxies are fainter and smaller, but they're aligned along a diagonal line that suggests they are part of a filament. The team believes this filament will eventually evolve into a massive cluster of galaxies, much like the well-known Coma cluster in the nearby universe. This discovery is one of the earliest filamentary structures ever found associated with a distant quasar, and it challenges our understanding of how the cosmic web forms and evolves, because it shows that such structures can exist at very early times when the universe was still young and chaotic. It also provides clues about how the earliest black holes grew and influenced their environments. The JWST is opening new windows into the early universe and its mysteries. By identifying the earliest strands of the cosmic web, it's revealing how galaxies and clusters emerged from primordial fluctuations and how they shaped the structure and evolution of our universe. Now, while it may not be obvious, the James Webb Space Telescope is a powerful tool for studying the chemistry of the universe, especially the formation of complex carbon-based molecules that are essential for life. One of its most remarkable discoveries is the first detection of a crucial carbon molecule called methyl cation in a planet-forming disk around a young star. Now, if you wonder what methyl cation is, it's a simple molecule that consists of 1 carbon atom and 3 hydrogen atoms with a positive electric charge. It is important because it aids the formation of more complex carbon-based molecules by reacting with other small molecules, even at low interstellar temperatures. Scientists have predicted that methyl cation is the cornerstone of interstellar organic chemistry, but until now, it has never been seen in space. The JWST detected methyl cation for the first time using its near-spec and mid-infrared instrument to observe a star system known as D203506, located about 1,350 light-years away in the Orion Nebula. This system consists of a small red dwarf star and a protoplanetary disk, a disk of gas and dust where planets can form. The system is exposed to strong ultraviolet radiation from nearby, hot, young, massive stars which can affect the chemistry of the disk. The detection of methyl cation was confirmed by observing a series of key emission lines from the molecule in the infrared spectrum of the disk. These emission lines are like fingerprints that reveal the presence and properties of the molecule. The team also detected other molecules in the disk such as water, methane, ammonia, and hydrogen cyanide. This discovery is significant for several reasons. First, it validates the incredible sensitivity and resolution of the JWST, which can detect faint signals from distant and complex sources. Second, it confirms the central role of methyl cation in interstellar chemistry and shows how it can form in different environments. Third, it provides clues about how organic molecules can form and evolve in planet-forming disks, and how they can be affected by ultraviolet radiation. But one of the telescope's most remarkable discoveries is that galaxies transformed the early universe by clearing the gas around them and making it transparent. The early universe was a very different place from what we see today. The gas between stars and galaxies was opaque, meaning that energetic starlight could not penetrate it. This made it difficult to observe the young galaxies that were forming in the aftermath of the Big Bang. But about 1 billion years after the Big Bang, something changed. The gas became completely transparent, allowing light to travel freely across the universe. This dramatic transition is known as the era of reionization, and it marks a key milestone in the history of our universe. But what caused this transition? How did the gas become transparent? These are some of the questions that astronomers have been trying to answer for decades, and thanks to the JWST, they've finally found some definitive evidence. By analyzing new observations from JWST, a team led by Simon Lilly of ETH Zurich in Switzerland found that galaxies that existed 900 million years after the Big Bang ionized the gas around them, causing it to become transparent. They also used Webb to precisely measure the gas around the galaxies, identifying that bubbles of ionized gas have a 2 million light-year radius around the tiny galaxies. Over the next 100 million years, these bubbles grew larger and larger, eventually merging and causing the entire universe to become transparent. This discovery proves that galaxies were responsible for reionizing the universe and shows how they transformed the early universe by clearing our collective view. The stars in these galaxies emitted enough light to heat and ionize the gas around them, creating huge transparent bubbles. And the JWST also revealed some surprising details about these early galaxies. They were more chaotic and complex than those in the nearby universe, showing signs of active star formation and supernova explosions. They also had different shapes and structures than expected, including elongated features and clumps. These findings challenge our understanding of how galaxies form and evolve and show how JWST can reveal new aspects of the early universe that were previously hidden from view. By studying these ancient galaxies, astronomers can learn more about their masses, ages, histories, and compositions and how they influence their environments. And then there is the JWST Advanced Deep Extragalactic Survey, or JADES, which is an ambitious program of infrared imaging and spectroscopy in the two premier extragalactic deep fields, Goods South and Goods North, designed to study galaxy evolution from high redshift to cosmic noon. JADES is one of the largest programs in Webb's first year of science, using about 770 hours of Cycle 1 guaranteed time from the NIRCam and NIRSpec instrument teams. JADES has already accomplished several remarkable feats, such as discovering hundreds of galaxies that existed when the universe was less than 600 million years old. These galaxies are among the earliest and most distant ever observed, and they provide clues about how the first stars and galaxies formed. But how did JADES discover these ancient galaxies? The key is JWST's sensitivity and resolution in the infrared. The infrared is a part of the electromagnetic spectrum that has longer wavelengths than visible light and is invisible to the human eye. The infrared is important for studying the early universe because the expansion of the universe causes light to increase in wavelength as it travels across vast distances. This means that light from very distant objects is shifted to longer wavelengths, or redshifted, making them appear redder than they actually are. The more distant an object is, the more redshifted its light becomes. JWST is designed to observe infrared light, which allows it to see objects that are too faint or too redshifted for other telescopes. And Webb can also resolve small details in these objects, revealing their shapes and structures. By using NIRCam and NIRSpec, JADES was able to detect hundreds of galaxies that emitted light when the universe was less than 600 million years old. These galaxies have very high redshifts, ranging from 7 to 12, meaning that their light has been traveling for more than 13 billion years to reach us. So what do these ancient galaxies look like? They are very different from the galaxies we see today. They are much smaller and fainter, with masses of only a few million to a few billion times that of our Sun. They're also very young and active, with many hot, massive stars forming within them. These stars emit ultraviolet light, which ionizes the gas around them, creating huge bubbles of transparent gas. These bubbles, as talked about earlier, eventually merge and make the entire universe transparent in the process known as reionization. But why are these ancient galaxies so important? They're important because they tell us about how the first stars and galaxies formed and how they influence their environments. They also tell us about how the universe evolved from a dark and opaque state to a bright and transparent one. By studying these ancient galaxies, JADES can answer some of the fundamental questions about the origin and evolution of the universe, such as how did the first stars and galaxies form, how did they reionize the universe, how did they grow and change over time, and how did they shape the structure and history of the universe. And apart from all this, JADES has also revealed complex structures and shapes in some early galaxies. These galaxies were more chaotic and diverse than those in the nearby universe, showing signs of active star formation, supernova explosions, mergers, and clumps. And JADES has also measured the size of closer galaxies. These galaxies are more mature and evolved than the early ones, and they show how galaxies grow and change over time. And JADES has also extended Redwood via coordinated parallels with the MIRI. MIRI provides complementary information about the dust and gas in the galaxies, as well as their stellar populations and environments. JADES is opening new windows into the early universe and its mysteries. By using Webb's unprecedented sensitivity and resolution in the infrared, it's revealing new aspects of galaxy formation and evolution that were previously hidden from view. JADES is also providing a rich legacy dataset for future studies by astronomers around the world. As we continue to explore and learn more about this amazing place we call home, we can only imagine what other amazing discoveries await us. Now, one of the ways that Webb proves the formation and assembly of galaxies is by observing a protocluster of 7 galaxies that existed when the universe was only 650 million years old. This protocluster is one of the earliest and most distant ever confirmed, and it provides clues about how galaxies clustered together in the early universe. JWST used its NIRSpec to measure the velocities of these 7 galaxies and confirmed that they are bound together in a protocluster. These galaxies are moving at very high speeds, more than 2 million miles per hour, within a halo of dark matter. The dark matter is an invisible form of matter that makes up most of the mass in the universe, and it acts as a gravitational glue that holds galaxies together. And JWST also used its spectral data to model and map the future development of the protocluster all the way to our time in the modern universe. The prediction is that the protocluster will grow in size and mass and eventually resemble the Coma cluster, a monster of the modern universe. The Coma cluster is one of the largest and densest galaxy clusters known, with thousands of members. This discovery proves that galaxies formed and assembled in clusters very early on in the history of the universe, and that these clusters evolved over billions of years to become the massive structures we see today. And it also demonstrates how Webb can use its sensitivity and resolution in the infrared to detect and study faint and distant galaxies that are beyond the reach of other telescopes. Another way that Webb proves the formation and assembly of galaxies is by observing their shapes and structures at different distances and redshifts, which correspond to different epochs in the cosmic history. By looking back in time, JWST can trace the evolution of galaxies from their infancy to their maturity and compare them with those in the nearby universe. For example, JWST has revealed complex structures and shapes in some early galaxies that existed when the universe was less than 600 million years old. These galaxies were more chaotic and diverse than those in the nearby universe, showing signs of active star formation, supernova explosions, mergers, and clumps. These features indicate that these galaxies were undergoing rapid growth and transformation driven by gravity, gas inflows, feedback, and interactions. JWST has also revealed more regular shapes and structures in some closer galaxies that existed when the universe was about 1 billion years old. These galaxies are more mature and evolved than the early ones, and they show how galaxies grow and change over time. They are larger and brighter with different types, shapes, colors, and compositions, and some of them are part of protoclusters, which are groups of galaxies that will eventually form massive clusters. And the JWST has also revealed more diverse shapes and structures in some even closer galaxies that existed when the universe was about 2 billion years old. These galaxies are closer to those in the nearby universe, but they still show some differences. They are more numerous and dense, indicating that galaxy formation was very efficient at this epoch. They're also more dusty and gas-rich, indicating that star formation was still very active. This discovery proves that galaxies formed and assembled with different shapes and structures at different epochs in the history of the universe, and that these shapes and structures reflect their properties and processes. It also shows how JWST can use its imaging capabilities to resolve small details in distant galaxies, revealing their morphology and complexity. And one of the never-before-seen parts of the universe that JWST has revealed is Pandora's Cluster. Pandora's Cluster, also known as Able 2744, is located about 3.5 billion light-years away from Earth. It is one of the most complex and violent regions in the universe where galaxies collide and interact with each other, creating shockwaves, gravitational lensing, and extreme temperatures. Pandora's Cluster has been studied before by other telescopes such as Hubble and Chandra, but JWST has revealed new aspects of this cosmic spectacle that were previously hidden from view. One of the new details that JWST has uncovered in Pandora's Cluster is the hundreds of distant lensed galaxies that appear like faint arced lines in the image. These galaxies are much further away than Pandora's Cluster, but their light is magnified and distorted by the massive gravity of the cluster, which acts like a giant magnifying glass. JWST's sensitivity and resolution in the infrared allowed it to detect these faint and redshifted galaxies, some of which were seen when the universe was less than 1 billion years old. Another new detail that JWST has uncovered in Pandora's Cluster is the distribution and composition of the gas and dust in the cluster. The gas and dust are heated and ionized by the collisions and interactions of the galaxies, creating a hot plasma that emits X-rays. JWST's MIRI, however, was able to observe this plasma in infrared wavelengths, revealing its temperature, density, and metallicity. JWST also observed the cold dust in the cluster, which is associated with star formation and galaxy evolution. And a third new detail that JWST has uncovered in Pandora's Cluster is the diversity and complexity of the galaxies in the cluster. The galaxies in Pandora's Cluster range from giant ellipticals to dwarf irregulars, and they show different signs of activity, such as star formation, supernova explosions, black hole accretion, and mergers. JWST's NIRCam and NIRSpec were able to observe these galaxies in detail, revealing their shapes, colors, sizes, masses, ages, histories, and compositions.